Hi, Zin. Welcome back. Hope you're doing well. Irvin, welcome back. Hey, Santino, good morning. Welcome. Hello, Kim. Welcome. Hey, Nadal. Good morning, Faith. Hi, Micaiah. Welcome back. Hello, John. Welcome back. Got your email. I'm not sure why it didn't save, John. We have till Wednesday. Try it out. Figure it out. Let me know if you need help with that, all right, John? Bad connection. Sometimes that does it. On table I. You have till Wednesday to get that back into me. Maybe it's bad connection. I'm not sure what's going on with that. But I did notice a couple of assessments on your exit passes from solutions. Not completed, so if you need to talk to me more, please let me know during the breakout room. Hi, Joey G. Welcome back. Hey, Asim, welcome back. Hey, Tintin. Good morning. Hey, Emma. Welcome back. Hey, Nadina. Good morning. Hi, Bowman. Mike. Hi, Michael. Welcome back. Hello, Kai. Hello, Alan. Welcome back. Frank, welcome back. Oh, well. Get on top of it, Joey. Yeah, let's get them done by today. That's the last straw for that one. I have to keep going back and rechecking stuff when that happens, so I'll make a note by yours. You're done. Yes, Bellman, by today. Or by tomorrow, I have to say. It's got to be done by tomorrow morning. Grades are due this week. Hi, Jumila. Welcome back. Hi, Phil. Welcome back. Hope you're doing well. Leonardo. Welcome back, Leonardo. You're doing well. Welcome back. Hey, Wendy. Welcome back. Alex. Welcome back. All right, welcome back. I hope you're all doing well, staying safe, staying warm, and getting ready for this little heat wave we're gonna have here. So next 7 days looks good for us. Here's a little forecast from WKTV. You can see what's going on. Spring is starting to get in the air. It is true. March comes in like a lion, out like a lamb. Every year it's like the same thing. I feel like beginning of March is horrible. You have a big snowstorm. End of March usually starts to really turn to like nice spring weather. So you can see what's ahead for us this week. Get those jogging shoes, sneakers all dusted off. Those walking shoes ready. Take advantage of this forecast. We live in central New York. You never know what's going to happen next week. So take advantage of the next couple of days. Today it's going to be nice out. Sunshine out there. Get out there, get a little routine, get a little workout in, jog, walk, bike ride, whatever it may be. Get a little sanity for yourself, fresh air. All right, happy International Women's Day as well. Ladies, happy International Women's Day. And a couple other things. Let's looking for just Joseph and Tristan. If you are here, please let me know. Joseph and Tristan. All right, a couple things. The 5 weeks is due. It's going to be over with. I have to have my grades in by Friday. I'm going to throw it out there to anybody that did not complete all their exit passes or assignments. Throw it out to everybody right now. I'm giving you guys till Wednesday morning, 8 o'clock, really Tuesday night, to make up any exit passes that you had to complete. So any exit passes that you need to complete, please get those done by tomorrow night. What is going to be graded for the quarter so far? 5 weeks. What do we cover quarter 3 so far? Basically, we started talking about unit 6. So anything here. We talked about unit 6, which was solutions. So there's table F, soluble versus insoluble. Actually, you guys all did those. Guided notes have to be turned in. Those have to be turned in. Make sure those are completed. If you didn't do that, then it's going to really hurt your grade. Actually, I'm not sure everybody did all these. So topic 2A, because I put zeros in there if you didn't do it. 2A, table F, soluble versus insoluble. Solubility curve exit pass, molarity exit pass, ppm exit pass, percent composition exit pass, your guided notes, and colligative properties exit pass. That's unit 6. And we also started on unit number 7 within this quarter as well, which was kinetics. Whoa. Darn it. Sorry, I didn't want to show you your grades. Kinetics. Topic 2 was PE diagrams. Topic 3 is exo and endothermic reactions. Those had to be completed. Someone just did it. Thank you. And table I, which was the worksheet you had to do. You had to figure out the reactions, exo, endothermic reactions, all that stuff. And that is all that's going to be graded for quarter number 3 so far. Anything right there. Exit passes from basically unit number 6, exit passes for unit number 7, and your guided notes and table I. I gave you a lot of time to work on these in class throughout the last couple of weeks, last few weeks. So if you're not doing them, I don't know what's going on with you at home. If you need to talk about something with me, you're more than welcome to. But that is a lot of assessments. Each topic has an exit pass that you should be able to complete, should have done already. Any questions on what I'm grading for quarter number 3? If you did them well, you're in good shape. If you missed a few exit passes, going to hurt you. You missed one, it's going to hurt, but not as bad as missing like 5 or 6. So again, check your own record, make sure it's completed. Wednesday, I am going to finalize my grades, put them forward, move on forward with this next 5 weeks. So by end of Tuesday night, Wednesday morning, let's just start grading right away. So that's fair game to anybody. If you have to get something done, get it done. I'm not going to take off points. So last warning, you guys are really pushing it to the last week here. So moving on. All right, let's figure out what's happening for today. COVID report for today. Here's Oneida County dashboard. We have 553 active cases of COVID in the county. Last week we had 570, so we're definitely decreasing. Resolved cases, there's 18,695 resolved cases. That number of deaths has not changed. So that's a good sign. You can see there's 29 people in the hospital and 5 people in ICU. Steady, decreasing a little bit. Number of vaccines are starting to increase. That's good. The more people that get vaccinated, the better off we will be as a community. We'll have this more under control, the virus under control here. Here's the daily positive numbers. Last week's data, not bad. Looks like a little increase as the week progressed, but not a huge increase. The numbers, crunch those numbers. 32 on the 6th. Day before it's 33. Day before that it's 38, 32, 28, 24. So all that data had numbers that were below 40. That is a great sign. So less than 40, those numbers. Here's my 40 mark. And all those values were below 40. When was the last time we had a week below 40? Check it out. If we're checking it out now, last time we had a week below 40. Last time before below 40. No, that was our peak, January 1st. Definitely not below 40 here. Looks like the last week below 40 looks this duration. What was that time frame? That time frame was before Halloween. So October, November, that was the last time we had less than 40 cases throughout the duration of a week, a whole week span. So that is a good sign. Hopefully we can replicate what happened before Halloween in the summer. Hopefully we get back on that routine of the state. Hopefully we continue with that next. Hopefully that's what this week or the next week has in store for us. If you cut this peak in half, cut that peak rate in half on January 1st. Hopefully we mirror, hopefully copy, reflect that image to the left and have it for the next few weeks. Excuse me. That granola bar just got stuck in my throat earlier. All right, so hopefully we mirror that image. That would be a good sign. All right, moving on forward. There's a COVID report. Stay informed. Another thing to note, elementary students, your younger brother, your cousin, whatever it may be, today's their first day live and in person. If you have a younger brother, cousin, sister, whatever it may be, and they're in cohort A, they had the ability to go to school today. If they're in cohort B, they have the ability to go to school Thursday and Friday. If you don't know what I'm talking about for your younger brother, younger sister, have mom, dad, grandma, whoever's at home, have them call up the school and figure out what cohort they're in. All right, so there's some housekeeping for today. Let's move on forward, figure out what's going on for chem class for today. Daily agenda. Quote of the week comes from Albert Einstein. The people who think they are crazy enough to change the world are the ones who do. So set yourself some goals. Set the bar high for your goals. Go out there, change the world, make a difference each and every day. You have one life to live, you might as well make the most out of it. Being impact to society. All right, Monday, March 8th, 2021. Today's a day 2. Oh, I will not see you tomorrow. So tomorrow, make sure you work on getting those exit passes completed. Please make sure they're done by tomorrow. We are continuing on with unit number 7, kinetics and equilibrium. We'll start off with a warm-up, and then we'll get to topic 4. We'll get to equilibrium today. That's my goal, equilibrium. My goal is to finish up equilibrium notes and just play this video. And then on Wednesday's class, we'll go through examples, and I'll give you time for the exit pass as well. Before I jump into the warm-up, let's play that game again. I'm having fun with that game. Let's do a little review process for today. So here we go. Once you have an answer, it asks that you try your best to come up with an answer. Try to pick it out from the beginning of the year. Pull it out of the brain. Put it in the chat, and I'll give you like 15 seconds, 20 seconds for each question, and we'll move on. So I'm not going to give you a ton of time to think about it and respond, but 20 seconds should be enough for like a rapid fire review process. This review is coming out of unit number 2. Once you have an answer, please put it in the chat. Just get my stopwatch rolling here. 20-second stopwatch. Question number 1, what is kinetic energy? Give it a shot. Put it in the chat once you think you know what kinetic energy is. What is kinetic energy? Thanks, Alex. Oh, you are here. Weren't you absent, didn't I? 4 seconds over. Oh, you're here. Cool. A lot of awesome answers. Thank you. Energy, emotion, energy, emotion, energy, emotion, energy, emotion, energy, emotion, energy being used, energy of movement, energy that a body possesses, and virtue of being in motion. Nice. Energy from motion of an object. Kinetic energy is energy in motion. Next question up. Here we go. 20 seconds. You need 15 or 10. Which phase has the greatest kinetic energy? 20 seconds. Here we go. Which phase has the greatest kinetic energy? Which phase has the greatest motion? Easy one. Everybody put the same answer there. Gases have the greatest kinetic energy. Next question. Define temperature. How do you define temperature? What is temperature? Kind of. Oh, nice, Alex. A little vague some of these answers are. A couple good answers. In chemistry class, we define temperature as the average kinetic energy of particles. So the average kinetic energy of particles is temperature. Average kinetic energy of particles, temp. Next question. What's it called when you go from a solid to a gas? Solid particle to the gas particle. It's called what? I don't judge on spelling. Nice. Tintin, Santino, thanks. Faith, yep. What's it called when you go from a solid to a gas? Yes, in? Emma, yep. Close. Sublimation. Sublimation, long word. Solid to gas. Sublimation. Solid directly to a gas. Next question. In terms of heat, what's it called when a particle changes from a solid to a liquid? Question is, in terms of heat, what's it called when a phase changes from a solid to a liquid? In terms of heat, what's it called when something changes from a solid to a liquid? In terms of heats of, yes, Jordan, nice. Yes, Kai. So you guys are giving me the other word, transition. Yeah, from a solid to liquid, it is going to be called sublimation. I'm sorry. Solid to liquid is heat of fusion. Yes. A lot of you guys have it. A lot of you guys put melting initially. Vaporization. Should be heat of fusion. Fusing something together from a solid to liquid. It's going to be a portion of the curve, that flat line, heat of fusion. Control stopwatch here. All right, next question. What is an ideal gas? What is an ideal gas? 20 seconds. What is an ideal gas? Yes, Adina. Ideal gas. Yes, Alex. Ideal gases are high temp, low pressure. Conditions for an ideal gas, high temp, low pressure. High temp, low pressure. Ideal gas, high temp, low pressure. Next question. What are two liquids on the periodic table of elements? What are two liquids on the periodic table? Give me a symbol. You give me the name. Cool. Nice. Yes, John. It's one of them's in. Two liquids on the periodic table of elements. Mercury and bromine. Mercury and bromine. Two liquids on the table of elements. Next question. What in Celsius, degrees Celsius, what temperature does water freeze and what temperature does water boil? In degrees Celsius, what temperature does water freeze? What temperature does water boil? 20 seconds. Here we go. Cool. A lot of you guys know this. Water freezes at 0 degrees Celsius. Water boils at 100 degrees Celsius. So that was from Unit 2 as well. Last one. What is a kinetic molecular theory for gas? There's like 5 different things for a kinetic molecular theory of a gas. It basically said how gases occupy space, how gases travel. What are some things that occupy kinetic molecular theory for gases? What is a kinetic molecular theory for gases? 20 seconds. Put one down, put 2, 3, whatever you know. How do gases travel? Yes. 1. How do gases travel? Nice. Yeah. Definitely a tough one. So far, with that 20 seconds, they take the shape of the container. That's one of them. I'm not sure about temperature. Someone put temperature, but we'll scratch that one. Gases do not attract each other. That's another one. They spread out, take the shape of the container. They move in, gas particles are random, constant motion. They move in constant motion, straight line motion. Good. When gas particles transfer energy, they transfer all of their energy. It's called elastic potential energy. Transfers all of their energy. And really, those are the main things you should be aware of for gases. All right, thanks for playing in that review session for unit number 2. That was mainly on energy and matter and energy. Let's move on forward. I do like playing that. You guys interact a little bit better. Sometimes I feel like with the random stuff and the rapid fire. Missed that from class. All right, so please open up the warm up. It's 3-8-21 warm up on Unit 7, Kinetics and Equilibrium. Please click on this. And there's 12 questions here from topics 1 through topic number 3. Kinetics, potential energy diagrams, and exo and endothermic reactions. I'm going to ask you to work on this for 12 minutes. I'll give you a minute per question. I'll put you in breakout rooms. Alex, you want to have partners or independently for this assessment? Breakout rooms by yourself or with partners? Alex Brown, do you want independent breakout rooms or do you want to work with a partner? Your call. Gregory? No? All right, Alex, took too long to answer. Tintin, you want partners or independent?
Independent.
All right, please work on the assessment. I'll give you 12 minutes to work on it. At the end of 12 minutes, we will go over it. Please try your best. Whatever you put into something is what you get out of it. If you have questions, the breakout room is a perfect opportunity to ask questions to me independently. Give it a shot. Please join your breakout room. 12:18 we'll review. 12:18. Hey, John, I just wanted to see if you had any questions for any of the work you had to make up or any questions with that document.
No, I don't have any questions.
Right, you have like, I don't know, there's a handful of exit passes you're missing, okay?
Oh, okay. Okay, I'll check those out.
Check them out. I think a more majority of them are from unit number 6, which is solutions. So I did notice that. I don't know if it's a problem with your technology, connection. I'm not sure, but if you need help, let me know, okay?
Okay, thank you.
No problem. I need them done by Tuesday night, okay?
Yeah, I will.
All right. All right. Bye bye.
Bye.
Okay, another 5 seconds, we'll get rolling. All right, hopefully a chance to go through a majority of those questions at least for the warm-up. A lot of these questions are from the last few topics. Here we go. Question number 1. Let's cruise through this. Given the reaction CH4 plus 2 moles of O2 yields 2 moles of water plus carbon dioxide. That's the reaction we did last time in class with a whoosh bottle. So you should be familiar with what happened there in that reaction. But in case you don't remember what that reaction is, no big deal. On the reference table, you can find some chemical equations. So that chemical equation happens to be, again, the first one right there on table I. So you have this reaction, it says heat to the reaction at standard pressure, temperature, and pressure. You have a value of heat, which is negative 890. Once you find that the value of heat is negative, you know it's either A or C. It's definitely not positive. It's not going to be B. It's not going to be D. And the heat is negative. Since it's negative, you should be able to understand all the way to the bottom. Negative sign indicates it's an exothermic reaction. So it's got to be exothermic reaction. That means it's going to be heat is released. Number 1, the best answer is C. If you have a chemical reaction on the regents or a question you might have, if it's a reaction, you might be able to find it on table I. There might be some questions on heat or energy. You definitely have to check out table I. It did not tell you to check out table I, but you can access that table. 1 is C. 1 is C. Next up, number 2. Given the reaction S plus O2 yields SO2 plus energy, which diagram best represents the energy change for this reaction? Please record your answer in the chat. Energy's on the right side. Thank you. Common answer, lots of A's. We have a reactant. There's my reactant. Yields, forward reaction. There's my product. Product plus heat. Product plus energy. Maybe it says 100 kilojoules. So reactant to product. My energy's on the right side. Therefore, it's got to be escaping. It's an exothermic reaction. Choice C is nothing like we saw before. You will not see anything like C throughout the year. Choice D is a little funky as well. Doesn't look like an exo or endothermic reaction. Choice A is the best answer. I told you, hey, think of a building, a 2-story building. You're on top of the world, on top of the building. And that building catches fire. What's going to happen? You're going to get the heck out of there. You're going to escape. You're going to leave. You're going to release from the building. This is an exothermic reaction. It goes from high to low. Release. Choice A, best answer for number 2. Number 3, moving on forward. B was an endothermic reaction. Number 3, which statement correctly describes an endothermic chemical reaction? Which one's an endothermic chemical reaction? Please record your answer in the chat. Which one's endo? Cool. A lot of B's. Good. B looks like a good answer. Products are higher potential energy. PE's on the y-axis. Products are higher potential energy than the reactants. Yes. And the heat is going to be a positive value. Definitely. That is a correct answer. So the heat value in the situation, delta H value, goes from the difference between the reactant and the product. So that interval represents delta H value. I do want to elaborate on this a little bit more. Delta H, what does that mean? It means the heat of the product minus the heat of the reactant. Let's take it another step further. Let's check out a couple of intervals. So we say I have this value. So I have this value. We'll say it's 20. We'll say that this is 10. I know it's a little crooked, but what are you going to do? So 20 kilojoules, we'll say. And we'll say this is 10 kilojoules. To analyze the delta H value here, it's going to be the heat of the product, which is going to be 20, and subtracted by 10. 20 minus 10 is a positive 10. So it's definitely a positive 10. Let's check out an exothermic reaction. Let's check out an exothermic reaction. Go high to low. Think it for a second. So it's going to go hot, high. Extend this beyond. And then it's going to dip down low. This is an exothermic reaction. The heat, delta H values, this is going to be 10. Delta H values, the products over here again, the reactants here. So for an exothermic reaction, it's going to be 10 minus, that's a reactant, 10 minus 20. Subtract those two values and you get a, hopefully you notice you get a negative 10. So there you go, negative, that's where the negative comes from for an exo. That's where the positive comes from for an endothermic reaction. That's how you calculate that work. That's where the change of heat comes from. So obviously that one, best answer is going to be B. 3 is B. Number 4, in the chemical reaction, the difference between potential energy between the products and the reactants is equal to what? Please put the answer in the chat. Yeah, awesome. Definitely choice C. Delta H, delta H. We didn't talk about anything else on this besides delta H. The only other thing we talked about throughout the duration of the year was delta T. This answer is delta H. You see potential energy diagrams. Hopefully that bulb goes off. We're not talking about delta G throughout the year. We're not talking about delta S. We saw change of heat when we talked about Q equals MC delta T, the heat. So we kind of saw that with heat. We did see that with heat, change in temp. That's what delta T is though. Choice C is the best answer. Number 5, potential energy diagram is shown. Which arrow represents change of heat of the reverse reaction? So reverse reaction, you're starting from the product. You're heading to the reactant. So reverse reaction. It's going this way now. Which one represents the change of heat? So we're following this flow this way. Where's my change of heat? Please put in the chat. This Faith, Tintin, yep. Several answers here. All right, let's check it out. So choice A is number 1. So interval number 1. That is referring to the bottom to the reactant. That is my potential energy for the reactant. So 1 is potential energy still for the reactant. Number 4, let's go to number 4. Goes all the way to the bottom, all the way to the top of the product. That is still my potential energy of the product. Number 3 would represent the energy needed to start the reaction all the way to the top. So activation energy, AE, is the energy needed to start the chemical reaction. Activation energy. Energy needed to start. We started here for the reverse reaction. We worked our way to the left. The change of heat is going to be interval 2. It's a difference between the reactant and the product. So that interval right there is my delta H. Is my delta H for my forward or the reverse reaction? So choice 2, best answer. 2 is the best answer. B is the best answer. Number 6 wants to know which letter represents the activated complex. Saw this one before. Please put in the chat. Complex, complicated. Roller coasters are complicated. Relationships are complicated at times. Gets a high point, gets a low point. A represents the potential energy of the reactants. Choice B is my complex. Choice C is the same exact interval as A. So that's my potential energy of the reactants to the right for some reason. And choice D is my PE and my products. Choice B, best answer. 6 is B. Number 7, chemical reaction occurs when reactant particles, what? Please put it in the chat. Yeah. So reacting particles, chemical reactions happen when the particles collide with proper energy, enough speed, enough kinetic energy, and proper orientation, direct hits. That gives you a chemical reaction. Choice C for number 7. Number 8, what occurs when a catalyst is added to a chemical reaction? What occurs when a catalyst is added to a chemical reaction? Please put in the chat. A catalyst is something that speeds up the rate of reaction. When a catalyst is added, what occurs? Michelle, a lot of you guys are responding are putting a lot of the same answers. That's awesome. Tells me you're retaining this information. There's an exothermic reaction. With a catalyst, I'm going to represent a yellow line. Nope, yellow does not come out very well. A catalyst is going to be a green line. The reactant's the same. The product's the same. The only difference is it's not going to get as high. So that interval right there is going to be a little bit different. It's definitely a different pathway. It has a different pathway there. A lot of C's there. So our responses I have are C's and A's. You can see that the reaction pathways are different there. There's a gap there. They're not the same pathways. There's going to be a different alternate reaction pathway, and there's going to be a lower activation energy. So a lower activation energy with that, a lot of you guys picked the same reaction pathway. If you submit it, if you submit your work, and it's going to say this is the right answer, but that is a mistake. It should be different alternate reaction pathway with a lower activation energy. Choice A is the best answer for number 8. 8 is A. 8 is A. Hopefully you saw that's a different pathway. Which intervals are affected by addition of a catalyst? If this were Regenstat, I would draw a catalyst in here. Reactant's the same. Product's the same. What's going to happen? It's not going to get as high of complex. Which intervals are changed with addition of a catalyst? Mark them up. My potential energy of the reactant is the same. Did not change. My product is the same level. No difference there. This would represent my change of heat. It's orange. Activation energy looks from reactant to the peak. That pink peak is different than the black peak. There's different levels there for activation energy. The same thing for the complex. The complex only goes to this mark instead of all the way to the top of the black. So which intervals are manipulated? Changing. Choice B, 1 and 3. What changes with the addition of a catalyst? Complex. Activation energy. Choice B is the best answer. Number 10, the reaction occurs more rapidly when 10 grams sample of Mg is powder rather than one piece. Because Mg powder has what? What's the best answer for number 10? So you take a chunk of magnesium and you break it down to smaller pieces, or powder. You break it up to powder. You file it to powder. Why does the powder react quicker? Yeah, more surface area, definitely. More surface area. The greater the surface area, the quicker the reaction is going to occur. More on reaction rates. Number 11, under which conditions will the rate of chemical reactions always decrease? How could you decrease the rate of reaction? Best answer, please, put in the chat. Decrease the rate of reaction. Yeah, you have to decrease the concentration and decrease the temperature. Decrease the concentration, decrease the temperature. It's going to slow down the rate of reaction. If you decrease surface area, if you decrease pressure for gases, that would slow down the reaction rate as well. Choice A is a good choice too. And last question, which ones increase the rate of reaction? Want to increase the rate of reaction? How are we going to increase the rate of reaction? Increase temp, increase concentration. D is the best answer. A lot of D's there. Nice job with that review. All right, so D is the best answer. Again, this warm-up you don't have to turn in. It's more for review for you guys. All right, moving on finally to new content for today's class. Please open up your guided notes. And we're going to take notes for probably the rest of class. Maybe a flick in there too, depending how quick we go. So please open up your notes. We're all done with topic 1, rates of reactions, effective collisions. You know those inside and out. We're done talking about the 4 factors that affect collisions: concentration, temp, pressure, surface area. We talked about potential energy diagrams. Should know those inside and out as well. Hopefully you have this memorized. And we started talking about equilibrium last time. So before last class, the only thing we talked about was a forward reaction, a reaction going in one direction. Now we're talking like 2 directions now. So equilibrium. So please open up your guided notes. We left off briefly talking about equilibrium. We said the forward and the reverse reaction happen at the same time. So it's kind of like going on a teeter-totter. You jump on a little teeter-totter, there's going to be like maybe a tire on the bottom. Sometimes there's a tire on the bottom. Zoom out for a second. Guess we'll draw quick. So you're talking about equilibrium. You go to the park. I don't see many parks that have teeter-totters anymore, but some do. Not many of them. Go to the park. Beautiful day tomorrow. And you hit up the park and you jump on one of these fancy things over there. Teeter-totter. So there's a couple teeter-totters. There's one like this, and then there's another teeter-totter there. Like this, like this. But sometimes there's like a tire on the bottom and it's suspended to like a piece of wood for the teeter-totter. So these are all different situations for working their way to equilibrium. On both sides of the teeter-totter, you're going to have 2 different people. We'll just call one side Ron and the other side Pam. Ron's here, Randy's here, and Paul's here, or Rebecca and Pauline. These are different chemical reactions. What happens here is they It goes through a reactant. The reactant has to form first to form a product. As it goes from the reactant to the product, it's going to balance off for a second. That teeter-totter is going to balance off for a quick second. But as it balances off, what's going to happen from reactant to products, there's eventually going to be more products. My whoosh bottle. Talk about my whoosh bottle now. You took the methane, you took the oxygen, and then what happened eventually? It went, so methane, oxygen, before I lit it, it stayed on this side. But once I lit it, it went and worked this way to balance. And then it worked this way after I lit it. What was left is just the product. So after I lit it, fire's gone. And then what was left for the product, just this product at the end. Equilibrium exists. It's going to be a fluctuation back and forth between the reactant and the product. My whoosh bottle was a one-way street. It only happened in one direction. If I were to cap this off or cork it off, then equilibrium could be reached. But the whoosh bottle in an open container is a one-way street. It's a forward reaction. I hope you like my little visual there today. Teeter-totters. All right, moving on forward. Let's go through some chemical reactions here. I'm really enjoying some of those diagrams, so what are you gonna do? All right, equilibrium. So we have this chemical reaction to analyze equilibrium. Before last class, we just talked about a forward direction, that top arrow on top, the one on top of the reverse reaction, whatever. And the forward reaction is going to be this, N2 gas plus 3 moles of H2. I'm going to paste it. I'm going to copy and paste it. You can rewrite it. Should have rewrote it. Yields, control, comma, control period. I'm sorry, control period. Oh, I'm messing up now. Think about that teeter-totter. Gas yields 2 moles of NH3 plus your heat. Your heat's going to be on the right side. It's an exothermic reaction. That is a forward reaction. Nothing crazy there. We already know that. That's a forward reaction. Goes from reactants to the products. The reverse reaction, it's going to go from the product to the reactant. So it's going to be in opposite order. I'll rewrite this one, give you a little bit more time to copy as well. So this situation for reverse reaction goes from the product, 2 moles of NH3 gas plus your heat yields 3 moles H2 plus N2. It's a shift back to the other side. Kind of like a yo-yo. Yo-yo goes up, down, up, down, up, down, up, down, up, down, up, down. It may stay down for a while. If you walk the dog, it might stay down for a while. But then it comes back up. Teeter-totter. Being balanced. Find that balance. The reverse reaction would be an endothermic reaction. So forward reaction, reverse reaction. I don't know if you can see that there. Represent equilibrium. It could be in either direction. You're trying to find that state of balance. For equilibrium, the quantities of reactants and product. Quantities of reactants and products are not necessarily equal at equilibrium. So the number or the concentration of the reactant and products are not necessarily going to be equal for equilibrium. What's equal? It's the rate of the back and forth shift that would be equal. So teeter-totter would be balanced for a second, but then it bounced back over. Be balanced for a second, but back over. At that balance point doesn't mean they're both concentrations are going to be equal. It's just a constant fluctuation back and forth between the reactant and the product. And next bullet is a rate of the two reactions. The forward and the reverse reactions that are equal. So the rate's going to be equal. Forward and reverse reaction that are equal. It's a constant shift back and forth, reactant to product, product to reactant, reactant to product. I don't know why there's not many teeter-totters anymore. I'm guessing too many injuries. Unequal shifting. Okay. Next up, we're going to analyze two different forms of equilibrium. We'll go through phase equilibrium. We'll go through solution equilibrium as well. We should have enough time to go through both of them. So on this heating curve right here, that's the heating curve. It goes from solid to liquid to gas. There's two different segments where equilibrium can be reached. Segments where equilibrium could be reached are going to be at BC, where there's melting or freezing, crystallization, heat of fusion, heat of vaporization. And it's also going to be from DE, where heat of vaporization, evaporation, condensation, those are the points for equilibrium. So phase equilibrium can exist from BC. It could be exist or can exist from DE. I see phase, I think of solid, liquid, gas, and solution equilibrium, or phase equilibrium, excuse me. Phase equilibrium happens when two phases coexist at the same temperature. Kind of like water. Water freezes at 0 degrees Celsius. Water at point B, it's working on being a solid. Water at point C, it's working on being a liquid. So at that temperature right there, that segment, you have two different phases existing. You have solid, you have liquid. If you go to -1 degree Celsius, you're now a solid. If you go to 1 degree Celsius, you're now a liquid. Same thing for DE. This is my boiling point for water, 100 degrees Celsius. At 100 degrees Celsius, you have a liquid at D. At E, you're just about to get to gas. So at this segment right here, you have two different phases. You have obviously liquid, you have gas, heat of vaporization. So we're really analyzing those flat points on that curve. At equilibrium, the rate of evaporation and condensation is equal. Evaporation and condensation are equal. So phase equilibrium exists at heat of vaporization or heat of fusion. If you understand that little drawing on that heating curve that I talked about, that's the majority of what you need to know here for this topic, this portion. Physical equilibrium. Equilibrium occurs between physical processes such as change of phase or dissolving. And we'll talk about that dissolving soon, solutions. And it could be physical equilibrium or solution equilibrium within that. Physical or phase and solution equilibrium. Solution equilibrium. Last unit, we talked about solutions. There's a reason why I teach these units in this order. Phase equilibrium. Phase equilibrium can exist between the solid and liquid phase. segment BC. Of a substance. So I put the segment above where we're referring to. Phase equilibrium can exist in two different places. The notes should be reorganized a little bit, but I'll do that next year. So phase equilibrium can exist between a solid and a liquid, or a liquid and a gas. I threw segment DE up here as well instead of marking up my little curve there. So DE or BC, that's where phase equilibrium can happen. We define this condition being the melting point of the solid phase or freezing point of liquid phase. So melting point or freezing point is where phase equilibrium can exist. And I did talk about the example about temperature for water. At 0 degrees Celsius, Celsius. 0 degrees Celsius in a closed container, both water and ice exist. Closed container. I knew that's wrong. Celsius. Oh, there it is. In a closed container, both water and ice exist at the same time. So solid and liquid exist at the same time. Try it out. If you want to try this out at home, you have a thermometer. Try to turn your water into ice. Leave it on the table in a styrofoam cup. Try to keep adding more ice until you get close to 0 or to 0 degrees Celsius. That point where you have 0 degrees Celsius is the point of equilibrium. And we would have done this in class for lab. I don't think I told you that the school changed their, they decided to not hold lab minutes for the regents this year. So from this point forward, we don't have to worry about 1,200 minutes, lab minutes, in order to take the regents. So I guess that's good and bad. It's good that we can really just focus in on content right now. It's bad because you're not going to have the hands-on experiments that come along with chemistry. Yeah, I told you guys I'd wait to do it when you guys return, but the content at this point, I think, is going to be more important than doing the hands-on labs in this environment. So it's definitely tough to incorporate all that stuff. So I apologize, but at least you'll have the content and you'll be prepared for the regents still, if we have that regents. No word on that yet. All right, some of the ice is melting and some of the water is freezing. In an equation can be written to show that both the forward and the reverse processes are taking place. So in this reaction, you have water as a solid and water as a liquid. This equation right here, equilibrium equation right here, for water would say you have water as a solid and in a liquid, or liquid and a solid. You should see that they're the same substance, but different phases. That tells me it's going to be phase equilibrium. The phases are different, but they're equal. Phase equilibrium. The compounds are the same, the phases are different. Phase equilibrium happens right there. Okay, I have 10 minutes left. I just want to go through solution equilibrium. Solution equilibrium we talked about. We talked about this curve before. We said, hey, this curve, solubility chart, solubility graph, we talked about this curve in terms of saturated, unsaturated, or supersaturated. Within this curve, we said a couple things. We said there's my y, there's my x. We analyze a curve, maybe some KCL. So there's some KCL. And then we said when something's underneath the curve, we said it's going to be points underneath that curve. It's unsaturated. We said a point that's on the curve is going to be saturated. Cannot take any more in or it's going to recrystallize. And then a point above a curve is going to be supersaturated. Supersaturated. You can see crystals there. The point we're talking about for solution equilibrium is going to be on the curve. So on the curve is where you're not going to be able to take any more in. If you take one more drop of crystalline, it's going to recrystallize. Or opposite direction. If you add more, then it's going to work on getting to the point where it's at the maximum capacity. So the point of saturation is going to be the point of equilibrium. That's what we're focusing on for now. Solution equilibrium. Solids and liquid exist at equilibrium, in an equilibrium on or in a saturated solution. Solids and liquids exists in equilibrium in a saturated solution. So saturation, the point of saturation is going to be the point of equilibrium for a solution. We actually highlighted that in our notes for unit number 6 as well, but now we're going to make more sense of it. So the point of saturation, the point on the curve, saturation, is where equilibrium can be existing. Teeter-totter. Think of that teeter-totter again. You add more in, it's going to start to recrystallize. You don't add as much, it's going to dissolve. It wants to know where that point is where you can't add anything else in, or it's going to change it. For example, solid sugar or salt. Sugar we'll go with. When solid sugar is first placed into water, we know what happens. You take a pinch of sugar, you throw it into a pitcher, it's going to dissolve. The sugar dissolves. But no sugar is recrystallizing. So at the point where you just put sugar into a pitcher, it's going to dissolve. No sugar is going to be recrystallizing if there's a small amount of solute in there. When you add a lot of it, then it will start to recrystallize. No sugar is recrystallizing. And when the rate of dissolving and recrystallization are equal, the point when they're equal, they're balanced off of that teeter-totter, this is where equilibrium will exist. Point where dissolving and recrystallization are equal, equilibrium will exist. And the solution is going to be saturated. Long story short, the point of saturation is the point where equilibrium is reached. constant shift back and forth between dissolving and recrystallizing. Dissolving, recrystallizing. The point where it's at the maximum potential, no crystallization's happening, no more dissolving, that saturation point, that's where equilibrium is going to be reached. And this formula below could tell you about solution equilibrium. The question they may ask you on the regents is probably where is most common, is going to be where does solution equilibrium exist? And you're looking for something that says saturated. Point of saturation. Solution equilibrium exists in a saturated solution. I'll look for questions like that for you guys for review. All right, so C2H22O11 solid, as it yields to a solution, the solution to a solid, back and forth at equilibrium, this could be an example for equilibrium for a solution. All right, that's it for notes today. I'm gonna actually play a video too. It's a 3-minute video, probably till the end of class. After I'm done with that, I'll dismiss you guys. So please enjoy this video on chemical equilibrium. What is chemical equilibrium?
Say two people are walking down the street and they bump into each other. They'll just shake it off and walk on. Sometimes that happens with molecules too. They just bounce off each other and that's that. But what if two people were to bump into each other, and during that collision, one person's arm got severed and reattached to the other person's face? Now that sounds really weird, but it's similar to one of the many ways that molecules can react with each other. Two molecules can join and become one. One can split apart and become two. Molecules can switch parts. All these changes are chemical reactions, and we can see them happening around us. For example, when fireworks explode, or iron rusts, or milk goes bad, or people are born, grow old, die, and then decompose. But chemical reactions don't just happen willy-nilly. Everything has to be right. First, the molecules have to hit each other in the right orientation. And second, they have to hit each other hard enough, in other words, with enough energy. Now, you're probably thinking that a reaction just happens in one direction and that's it. Sometimes that's true. For example, things can't unburn or unexplode. But most reactions can happen in both directions, forward and reverse. There's no reason that our face arm guy can't bump into armless girl, reattaching that arm back to its original socket. Now let's zoom out a bit. Now let's say that you've got 1,000 people on the street, and all of them start with their limbs normally attached. At the beginning, every collision is a chance for person A to transfer an arm to person B's face. And so at the beginning, more and more people end up with arms attached to their faces or arms missing. But as the number of people with arm faces and missing arms grows, collisions between those people become more likely. And when they bump into each other, guess what? Normal appendage people are reproduced. Now the number of limb transfers per second forward will start high and then fall, and the number of limb transfers per second backward will start at 0 and then rise. Eventually they'll meet, they'll be the same. And when that happens, the number of people in each state stops changing, even though people are still bumping into each other and exchanging limbs. Now, how many people do you think there are in each state? Half and half, right? No. Well, maybe. It depends. It could be 50-50, but it could be 60-40 or 15-85 or anything. We chemists have to get our little gloved hands dirty. We're in a lab, so not really dirty, to figure out what the actual distribution of molecules is. Even though each of these limb transfers is a pretty dramatic event for the people involved, if we zoom out, we see population numbers that don't change. We call this nirvana equilibrium, and it doesn't just happen with chemical reactions. Things like gene pools and highway traffic show the same pattern. It looks pretty still from 30,000 feet, but there is lots of crazy stuff happening on the ground. You just need to zoom in to see it.
All right, guys, that's it for today's class. Have a great day. Enjoy the day off tomorrow. Enjoy a nice walk in the park, whatever it may be. Stay safe. Enjoy the weather. See you next time. See you Wednesday, guys. If you have work to do, please make sure you make it up by tomorrow night. Have a good day. Bye, Kai. Bye, Nadina. Bye, John. Get your work done. See you guys. If you have questions, feel free to hang out.